Hi there, this is just a quick video for those of you who are not familiar with the trick of even and odd functions and taking the integral of those and how they make life nice and easy for us, especially for our harmonic oscillator wave functions, which are in fact even and odd functions depending on the state that you're in. Okay, so just a quick overview of what we mean when we say even or odd function. So an even function has a definition where the function, your y of x or f of x, is equal to the same value for the negative of your x. So if we look here, this is a plot of an example of an even function. We get positive values for y, whether we're at positive x or negative x. Okay, so the hallmark of an even function is that it's essentially symmetrical about your center value. Okay, so when we're integrating an even function, we can say that the integral from 0 to whatever our bound is on the positive side of x is going to be the same as the integral from 0 to the negative bound of our x. So in that case, what's nice there is that if you have a situation where you need to take the integral of an even function over a full set of bounds, okay, so here negative infinity to infinity, let's just say that these are going, obviously not, but let's just say they're going from negative infinity to positive infinity, okay? So that integral over that full range of negative infinity to infinity would be the same as the integral from 0 to infinity times 2, right? Just due to our symmetry of that function, okay? That's handy because a lot of times you'll have an integral table and the integral will be from 0 to infinity or 0 to a limit and not the full range of negative infinity or negative of your limit to your limit. Okay, so in that case we have the trick of that being equal to 2 times the integral of 0 to infinity of your even function. Okay, so again, a lot of times you'll have the ability to get the result for this integral with these limits from 0 to infinity, but not these full limits. So all you'll have to do is take 2 times the result of that that function. Okay, so that's the trick for even functions. Again, they're symmetric functions about your center value. So for harmonic oscillators, remember our center value is always about x equals 0. Right, so for our 0 displacement, if you happen to change your center value, so if we think back to our particle in a box, those were not technically even functions, even though they are symmetrical because our box range was from 0 to a, but we could say that they were even functions, even or odd functions about a over 2. So if we considered our center to be a over 2, then we could think of our particle in a box wave functions as even and odd for that situation. Okay, so really the key is just to make sure that whatever you're calling your center there is at the center of your symmetry. Okay, so for harmonic oscillator, that's at 0 for us. So we would be symmetrical between the limits of negative infinity to infinity. Okay, enough about even functions. Odd functions are even better. Okay, so odd function definition here. Okay, so we get a positive value for our function when we have a positive value for x, and then a negative value of our function when we go to the negative values of x. Okay, so here what we want to kind of notice is that if we take, remember when we're integrating, we're taking the area under the curves, right? So if we take that area and add it to that area, what are we going to get? We're going to get 0, right? Because we've got our positive volume there, or sorry, positive area there, and we have the exact same negative area there. They're going to add up to 0. Okay, so what does that tell us about odd functions? Well, if we take the integral of an odd function over our symmetric space, again, remember harmonic oscillators get integrated from negative infinity to infinity. All right, so as long as you're symmetrical about your center, okay, with your bounds, you'll have that odd function behavior. If we integrate that, then we will get 0. Okay, so that's really nice. We don't have to evaluate anything in that case. So once you recognize whether your function is even, okay, you can use this trick. That will be helpful for some of your problems. Even better is if you have an odd function, right, and then you know that you have a result of 0. Makes your calculations very, very nice. Okay, so really the skill that you have to develop here is being able to recognize whether you have an even or an odd function. Okay, so just to relate this to our harmonic oscillator wave functions, our n equals even wave functions for a harmonic oscillator are going to be even functions. And if we have odd states, so if the n's are odd for our harmonic oscillator wave functions, then they are odd functions. So those are handy relationships to remember for your homework calculations. Okay, and then just a reminder of how your even and odd function math works. Okay, so inside your integrand, so if you have a couple of functions of x in here, okay, if you have an even function of x times an even function of x, you're going to end up with an even function. If you have an odd function times an odd function, you'll end up with even. So this is just like our positive and negative arithmetic. Okay, so odd number times an odd number gives you an even number kind of deal. So likewise, if you have an even function times an odd function, that's going to give you overall an odd function. Okay, so just keep all of these things in mind, these relationships between even and odd functions, and your handy tricks over here for evaluating even and odd functions, and your life will be oh so nice. All right, hope that was helpful. Put that to use in some of your homework problems.